Alright. So, different lighting. You'll be able to see the indicators, I hope. If not, let me know. Tonometer here, which we'll be using a little bit. Probes for that. These two prods are tied to these two clip leads. Just kind of scroll the way over here. And a number of capacitors to play around with. My stock bags full of the dang things. And picked a couple of random ones, and some I know a little bit about, which we'll get into in a moment. So, what's this thing do? Basically, it can measure three things about these capacitors. Now, I'm not even going to mess with the resistor measurement. It measures one thing, resistance. And I got 100 other things that can do that. But measuring these beasts is a little bit trickier, and there's also another aspect to it, particularly with the electrolytics, which I'll get into later. Alright, so it can measure, rather, the actual capacitance, and you can compare the reading you get to what's stated on the sleeve. It tests for leakage at its rated voltage, meaning leakage being as though there were a resistor placed from one end to the other, but it's actually inside, it's leaking between the two plates. You don't want that, never. So that it tests for leakage at rated voltage. It also gives you an idea of its electrostatic resistance, ESR. That would be as though you had a resistor in series with the capacitor, and you don't want that either. You want that to be as low as possible. Ideal capacitor would be nothing but capacitance, no inductance and no resistance. This can measure both the leakage resistance across the capacitor and any problems in the capacitor that appear to be a resistance in series with the capacitor, and that's what this power factor business is all about. It's odd that they referred to it that way, and it's the scale is 0 to 50 in percent, and it actually goes quite a bit beyond 50. We'll get into how that works shortly. There's a range switch. We're only going to be concerned with the 6 ranges of capacitance measurements. It goes from 0.0001 to 10 microfarad. Oh, I'm sorry. This is a multiplier. 0.0001 to 10. So here, set at 1, that would be 10, and then 1, and then 0.1, 0.01, and so on. It's kind of cool the way they have this scaled. If you've got, say, a 1 microfarad capacitor and you've got this set to 1, it'll dial in down here, but it's real touchy. It'll be a little bit tricky. So you can go up a range and still pull that 1 microfarad in. So you go to 0.1, the multiplier, 0.1, multiply it 10 by that, and you get the same reading, but the adjustment is much less sensitive, it's more forgiving, and you can really get it close in. More on that later. So anyway, start off, I'm going to test capacitance first. Usually what I do, the amount of power this thing puts into the capacitor is almost nil. So if it's complete short, it doesn't matter. It's not going to hurt the instrument. It's not going to hurt the capacitor. There's very low voltage across these, and so there's no worry about that. So I'm going to power this thing on now. This voltage control again has to do with the leakage tests, and also has another use for it, specifically for electrolytics, which we'll get into later. But for now, just turn the power on and keep his volume all the way down, and give it a moment for the tubes to heat up. Okay, hopefully you can see the eye tube's lit. And the way they have this set up with this dial set to 1 or anywhere really without any capacitor attached across this, the wedge stays closed. If you go below 1, it opens up all the way. I'm not sure if that was intended. It is kind of cool to test a quick check to see that, okay, the tube's operating right. You know, it's like a nice sharp open. So I would tend to, if I'm going to have this on for a little while, I would tend to leave that closed as it is, so that it evenly wears out the fluorescent target, phosphorescent target, whatever. You leave it like that, it'll burn that image in, and it'll get brighter where it's right now dark, and dimmer where it's right now bright, and it's noticeable. So if you're going to let it sit, I'd suggest, you know, just kind of close the gap there. You can see this tube's got some age on it, and I bought that tube new. You know, but it's working plenty well enough for my purposes here. So start off with what should be a very high quality capacitor. This is a Illinois condenser, Illinois capacitor. It's 1,000 volts. The tolerance is K, which I think was 20%. It's a 0.1 microfarad, 1,000 volt. The only thing we care about right now is the 0.1 microfarad. So clip him in. Alright. So 0.1, well, that should dial in, yeah, sure enough. See what this is doing. If I'm off, it closes completely. It'll open up right as I get to 1. And you see, it's kind of touchy, just barely touch it. So that's as open as it's going to get. It's nice and well defined, and it says on this dial 1.1, or actually it would be 0.11 because we're multiplying 1 by 0.1. Or I could go to the multiplier to 0.01. That'll mean that this will be 0.1 because I multiplied times 10. And sure enough it is. I would have liked it better if they put the damn tube over to the side so you didn't have to look through the dial pointer to see it. You know, these get a little dirty and fuzzy. But anyway, right there. Well, that's indicating a little bit lower. 0.096. Well, close enough. Certainly within tolerance of a capacitor that doesn't even have the tolerance on it, which probably means, well, it's K. Okay, yeah, there it is. K, tolerance. Plus minus 20%. Certainly falls within spec. So that's one test. And take a note that this power factor correction, let me put this back down, get this pointer out of the way, and get it real close as I can down here. Okay. This being set all the way to minimum, 0 in this case, 0%, and being able to get a very sharp opening of the eye tube is a very good sign. That means it's happy that this is a capacitor, not a capacitor in series with a resistor. Note that if I turn this power factor dial up, it begins to close that, and nothing I do can make it any better. It's you know, okay, peek it there and put this back down, and so that's an indication that this capacitor has a very low ESR, or at least as far as this instrument is concerned. Certainly acceptable in almost all cases. So far so good. But we don't know if there's any leakage across. Notice I'm touching this. There's no appreciable voltage on this. I'd be surprised if it was 5 volts. And of course, me putting a resistance, a leakage across it with my fingers changes the indicator. So you do have to be careful of that. So far, that's a good capacitor. Of course, it's brand new, and it's a modern one. I don't know when it was made, but I'm pretty sure within the past 10 years, judging from where I got it. So it's interesting, rather than have a switch to switch between leakage and leakage measurements and power ESR and capacitance measurements, they actually have you switch it to a different part altogether. This whole part of the instrument is dedicated to, it's separate and apart completely, other than the power supply. It's dedicated to checking leakage for capacitors, leakage across it. So plug them in there. Now this has 2 positions, actually 3. The position it's in now is discharge, and that means it puts a resistor across here, so that any capacitor that's tied across that is discharged. Safety reasons. This thing will charge a capacitor up to 600 volts, and you don't want to just disconnect it, because then you're holding a shock hazard, depending on its size, at least an inconvenience. So this toggle switch here is in the discharge position, meaning 0 volts across this, and a resistor across it to discharge it. So it has 2 other selections, electrolytic and mica and paper, which also would be any capacitor that's not an electrolytic. If it's a ceramic or a polymer of some sort, a polystyrene, mylar or whatever, that's this setting. And the difference between these 2 has more to do with the amount of current that's willing to allow to charge the thing. The electrolytics tend to be a higher value, a higher microfarads, and so it allows a bit more current to flow, and it's a bit more forgiving of leakage than it is when you have it set to the mica or paper or mylar or whatever it is you got. These are mylar. This is a Sprague orange drop. Should be familiar if you've ever done this stuff. I guess it's a polypropylene. Yeah, they have their uses. Another polyplastic capacitor, and some paper ones I have here, which we'll show. So what's across that right now is our golden capacitor. So what's the leakage on this guy? It's rated for 1,000 volts. So this thing can go only up to a little over 600 volts. That's fine. Usually you don't have to get to the full rated working voltage of these to discover trouble with it. So I'm going to turn the voltage on this all the way up, and it goes, there's 600 there as marked, and I've measured, I think it goes to 620 or something if you go past that. So we'll use that, and what's going to happen, I'm going to flip this up to mica paper, and this indicator is going to show if current is flowing through this capacitor, which it will do until it's finished charging. If it's leaking, in other words, if it has a leakage resistance across here, that will either just glow continuously or it'll flash. The way this, it's very interesting how they do it. The power supply in this thing puts very little current out here in this mode. And like I said, this what's it do? The 6Y6 tube. I think 6L6 with the slightly lower specs. It forms a power supply that you adjust the voltage output here, and it kind of regulates it to current through this neon indicator lamp. Pretty cool how they did it. So this is a discharge capacitor, evidenced by it's in the discharge position and connect it up. So I'm going to flip this to apply some voltage. Well, that didn't take long. One big flash. Let's do that again. Discharge it. Charge it again. So at over 600 volts, that capacitor is not leaking at all. There's no flash error. That capacitor will stay that way for a long time until something discharges it. In this case, it's going to be here ultimately. But just to show, I'm going to charge it up to something over 600 volts. Now grab this red clip lead, which used to go to here, and I'm gonna, so it was charged, it's now discharged. Connect it back, it's charged up again, put discharged. So this capacitor is, it's on, it's at the rated value, within 20% certainly, plus or minus 20% of 0.1 microfarad. It's not leaking, at least all the way up to 600 and some odd volts. No leakage across it. And it's also got very low ESR, this power factor, meaning that there's no, or very little series resistance involved with this. Well, there shouldn't be. This is going to be pretty decent quality capacitor, and it's new. It's never been used. So there's that. Oh, what else we got here? Oh, the famous, ubiquitous orange drop. Now this is also a 0.1 microfarad capacitor, plus or minus 10%. So this should be closer in value, or pretty doggone close. It should be within that plus or minus 10% of 0.1 microfarad. It's rated at 200 volts DC. By the by, some folks don't know this. Sometimes they put a mark on one end, a stripe, or dots like this, dashes. That means that this lead attaches to the electrode, the plate, the foil that's on the outside. Sometimes you get into a sensitive situation where it needs, the signal that's going into one end of it needs to be fairly well shielded. So this side would go toward the low impedance end of the circuit, for which into which the capacitor is put, or ground or something. Often you would see markings along these that say outside foil. This capacitor has just a band. It's maybe difficult to see, but that's what that means. It says that outside foil. Fairly common to do that, especially with the larger ones. Modern days, they don't really bother with that so much. But things are so small and the voltages are so low and they interact so little with one another because they're so small, it's just not necessary. So, but typically that would go to ground. So we'll follow that convention. It does not matter for this test. So there's our orange drop. Well, since we're already plugged into the leakage test, we'll drop this down to 200. That's his rated voltage, 200 volts, and go to like a paper. Same deal. Bang. Bit, bit, bop. Did you notice? It's flashing a little. There's not a bad capacitor. It's a useful capacitor. It's not as high a quality as this one is. That's Mylar. I'm pretty sure this is a polypropylene. Polyethylene maybe. I'd have to look it up. It's got a part or a type number on it. But anyway, perfectly, as far as leakage goes, it took a little bit. You notice it flashed a few times. It took a little while for the dielectric in these Mylar. It's like that. It took a little while for it to because of dielectric absorption. Fully charging the surfaces of the dielectric sometimes can take a little bit more or less, and how deep the charge penetrates into it. You know, Mylar is a pretty good insulator, but it's not the best thing in the world. These capacitors are, oh gosh, they're everywhere, and they're very useful, but they're not of the highest quality. I would tend to avoid using these orange drops in audio gear for that reason. She's flashing again. So there's some little bit of, I'm not even going to call that leakage. And that's at rated voltage. Now I can go up some, and I'm going to do so with this and see what happens. I'm going to take it up to 400 volts. See? Mylar, pretty good stuff. I'm twice the rated voltage at DC. Now there's no ripple current or anything like that, very little. If there is, it's so low current it's not going to matter. So I'll give it the full Monty. We go all the way up. So over 600 volts. This capacitor is withstanding that. Good old Mylar. It has its foibles, but it's also, as far as over voltage, it's forgiving. So I'm going to turn this back down and discharge the thing. Put him aside. There's another one. I don't know, just to show. Actually, I didn't measure the. Let me go back. I meant to measure the actual other parameters, characteristics of this guy. So we're back into measuring capacitance and ESR. So this is a 0.1. We should get a. Yep, we do. Right down there, 0.1. I'm going to set this to 0.01 and take this up to 10. Yeah, reads a little high. And not only that, you can't get a real well-defined full opening of this tube, of this wedge. It's a little blurry. Power factor. Crank this up a little bit. Oh, look at that. It comes right in. So, that this isn't to 0, that's not bad. It's at 5. What that's telling me is that not only is this capacitor, it takes a little bit of dielectric absorption issues, maybe some leakage, but it also has a small resistance in series with it, evidenced by this. It's not much, and in most cases, you know, for a $100 television set, who cares? It'll stay that way, you know, for a long time. These are fairly stable. I don't usually replace them when I see them out of hand, but these orange drops, you know, that's what they are. They're not very expensive, or they used to not be very expensive. This is an odd beast. This is a 10 microfarad. I'm pretty sure polypropylene. It's hard to see, 106K, so 10 microfarad, 20 plus my 20%, and it's rated at 100 volts. It's actually kind of amazing for something this size. But this is modern. This was purchased, oh gosh, in the past, I think 5 years, if not more recently than that. They turned out they couldn't use them, so I ended up with them. So what do we got? 10 microfarad. Let's put this to 1, so we should get it in about here. Let's turn the power factor off. Oh, look at that. Spot on 10. Power factor needs to be 0, which means has a low ESR, low series resistance. And the value is certainly within plus or minus 20% of 10. It's reading on this dial 10.1. I know this is not precisely calibrated, but for the purposes here, it's well enough, way well enough. So also I can go up a decade to 10, so that'll put the opening down here. And what this illustrates is that the dial is, at least in the ranges we've looked at so far, it's right on where it needs to be. There's not a single calibration pot in the thing. There's nothing. And to be this accurate with just relying on the accuracy of certain precision resistors and a couple of capacitors, even some pots, pretty doggone close. And I've checked it on all the ranges, and it's the same. Oh, so what's this guy look like leakage-wise? Okay, up here. Ooh, make sure our voltage is down. This is rated for 100 volts, so 100 volts it is. It's of a dry capacitor. And it's got a 10 microfarad, so it takes a little more time to charge it. Well, let's see. Will that stop eventually? You betcha. If it's a good capacitor, if it's not leaking. I have no reason to suspect that it is, but some of these plastic capacitors will do that. You have to watch them, especially of the larger value variety. I mean, 10 microfarad at 100 volts in this package is by itself amazing. What I'm seeing right now with this, I would not complain about. It's just still charging. Now, let me bump this up to 300 volts. Okay, so there's nothing wrong with this capacitor. I'm not suggesting you would use this in an audio path for you hi-fi guys like I am, but nothing wrong with this. Discharge. Actually, let's go for it. I've got bags of those things. All the way up to 600 volts. See what it does. Oh, just shorted. You might have even heard it. It went click. So, either that. Some of these self-heal. Let's stress it again. That's what's happening. It's internally shorting, blowing the short. See what's going on there? I hope you can see this pulsing. Gets up to a certain point, an internal arc takes place. It heals, begins charging again. The voltage gets too high, it arcs through again. I hope you can hear that. Click, click. And that will not hurt this instrument. It's hurting the capacitor. Now this capacitor is junk now. And every time that happens, it's vaporizing some of the luminization. And so lowering the capacitance. So that's this capacitor is being voltaged, and keeps charging up again to the too high a voltage, arcs through, and then heals, and immediately begins to charge again. It won't short. Not to say it can't, but what's happening now is it's not shorting. So if I go back down to, let's say, 300, now it looks like a capacitor again. Of course, it's got vaporized aluminum rolling around in it. So, discharge him. As I said, I got bags of this one, and they're not particularly useful, but this is junk. That gets, in fact, maybe I'll keep this as a demo piece. And this, it's pretty much the same. Just a different value, different voltage. I don't want to waste too much time. I want to get to the interesting stuff.